We are live, girls. Okay. Where would the electrons in this electroscope go if a positive rod came here? So let's put a positive rod over here. So a positive rod, it just says came near. Where would the electrons in the electroscope go? So it's not touching the positive rod, it's coming near. And, well, electrons are negative, opposites attract, so they go to A. Because opposites attract. Electrons will be attracted. The only thing that moves is the electrons. Good?
Can you do the one that touches?
Okay, sure. So, why don't we just do these and we'll get the ones that touch as well. So where would the electrons go if a negative rod came near? Well, the negative electrons would be repelled down to C because a negative field would make the electrons move far away. Now, how about touch? This is one you want, touch. Now, once there's touching, there's an exchange of electrons. Touch, negative rod. And electrons then naturally overflow into the electroscope because they always move to the least negative place or the more positive place. And so then what they do is they spread out in all locations, spread out evenly just to be away from each other. So they would go, what would happen? A, B, and C would be positive. I'm sorry, it would be negative because electrons, now there's no longer a balance in the electroscope, an equal number of electrons and protons. There's an imbalance where you have more electrons. And there you go. Now for positive rod, remember the only charges that can move are the negatives. So now a positive rod, and electrons can move in naturally, they'll want to be in a more positive place because opposites attract. So the electrons will travel into the rod, creating an imbalance in the electroscope so ABC would be positive. So, because the electrons would leave and then the net charge in the whole electroscope would be positive because there's no longer a balance of negatives and positives. All good. Number 5. So what happens where do the electrons go if the positive rod comes near? They go into C. The electrons, if that's a positive rod, well, what they'll do is try to get as close to the positive rod as possible. That's why they're going to go to A, because opposites attract and electrons move. Okay. Now this one over here, where the electrons go to get far away from the negative rod, they'll go into the ground, into the table. Say that again. Well, they can get even further away, it seems. If this was not touching the ground, I would answer B. But now they have ability to get really far away.
So they don't have the same size?
Yeah, they can actually leave. Yeah. All right. You've got this positive rod comes near. Well, what will happen? The positive rod comes near. Well, the electrons will be attracted to A because they know there's a positive field there. Opposites attract. So what happens? Let's see. What would the charge in A be? Well, if this is a positive rod, it would be negative because the electrons will be attracted over to A to be near the positive field. And B would be positive. That's why this answer is positive. Because if electrons leave B to be near the positive rod, it'll leave B positive. Okay, what would the charge on sphere be if a negative rod came near? What will happen is lights repel and the electrons will be repelled over to B because the rod is negative, they're negative, their lights repel and they move to B because they're repelled. Electrons repelled to B. And B is no longer neutral. It's got more electrons than protons, so it's negative. What would the charge in A be if a negative rod came near and at the same time B was moved away? A would be, let's see, it's a negative. A would be, so the electrons repel to B, leaving A positive. Because when electrons leave a neutral area, they make it positive. And that's it for that. Okay? Electrical charges quiz. What did you get for number one anyway? Let me switch. Oh, I think I lost my tango. Where's my tango? Oh, there it is, right there. Okay. So this is an excess of 2.5 times 10 to the 19th electrons, and each electron, so it's a with one electron, if you want its charge, is 1.6 times 10 to the negative 19th coulombs. So you have to, this is your conversion factor. You have to multiply that number by that number, the 2.5 times 10 to the 19th times 1.6 times 10 to the negative 19th. And what did you get, Jim? Choice four? Okay, very good. Now two, you're in electrical field and your charge is doubled. What happens to the force? Well, you can't relate two things on the same side. So you have to cross multiply. EQ equals F, cross multiply. And so if you double the charge, whoops, you double the force. See? Double, double, direct relationship. So you have to separate variables before you can relate them. Okay, number three. This is, here's a trick I was talked about before. Your answers actually tell you what to do. What are they telling you? They're telling you to take the newtons that they gave you, 0.06 newtons, divided by the charge that they gave you, 2 times 10 to the negative 6 coulombs. Now you've got to use parentheses. So 0.06 divided by button, parentheses, 2 times 10 to the negative 6, end of parentheses, enter. What'd you get, Gianna? Let's see if that's right. Good. Okay, number four. Two charges are separated by a distance of 1 meter, and they have a force of 9. What happens if you tripled it? Well, let's take a look at the equation about charges and distances, which is this. This is a very popular question on the Regents. These are change questions. So the top doesn't change, so it's a 1. The charge goes from 1 to 3. That's triple, so you plug in the change. But wait a second, r is squared. So this is 1/9 on this one side, 1/9 on the other side. Whatever happens to the right happens to the left. So what's 1/9 of 9? It's just 1. 1/9 of 9 is 1. So this is plugging in changes. So it's 1. Now, right away, I hope you should have canceled out things that when you're getting further away, it should get weaker. So you should cross out this and this, right? You have a 50-50 shot. So now, what you want to do 5 as well, right? Two charges. Let's take a look. This is another change question. It's about two charges and the force between them. This is the equation that you use. So the one of the two charges is doubled. What's going to happen to the force? Well, whatever happens to the right happens to the left. So one of the charges is doubled. The force is doubled as well. So there you go. 6. You're going from 1 meter. Two charges go from 1 meter to 0.5. That's half. What's going to happen to the force? Once again, this one's tougher. This is a change question. You're no change on the top. You're halving the bottom. 1/2 squared, though. So it's 1/1/4. Did you get this one? So this turns out to be 4. It's the inverse square relationship. 4 times greater. 1/4, 1/2 the distance, 4 times the force, inverse square. Okay, how much energy? W is required to Q and V. V equals W over Q. Look at the choices though. Wait a second, they're all in electron volts. That's a problem because J goes with C and E goes with E. I've got to change this to 2 elementary charges because E goes with E. The answers are in E. E goes with E, J goes with C. Now I can do it. 5 volts. W is unknown. Q is not 3.2, but 2 elementary charges. And cross multiply. 5 times 2 is 10. So it's this right here. You want to, well, what I said is, how did I get elementary charges in the coulombs? I said to myself, one elementary charge is 1.6. times 10 to the negative 19. I have 3.2. I have 2 elementary charges. Okay?
Would you ever have
To change the W, no. Okay, number 5, you have this much charge, Q, moving, and you have this much work, W. What's the potential difference? Let's see, well, J goes with C, so we're good. V is W over Q. V is unknown. W is 2.5 times, wait, that's not W. W is, whoops. W is 6.3 times 10 to the negative 4 joules divided by Q, which is given as 2.5 times 10 to the negative, well, that's sloppy, sorry about that. 2.5 times 10 to the negative 6 coulombs. 2.5 times 10 to the negative 6 coulombs, divide with parentheses. Did you do this, Gianna?
Yeah.
Could you give me the answer? B as in boy?
Yeah.
Seems like it's right. So now the energy to move, energy is W in electricity. To move one elementary charge, well, that's a problem. Look at my answers are in joules. Joules go with coulombs. I better go 1.6 times 10 to the negative 19 coulombs because J goes with C. So this is the V. So V equals W over Q. 5 volts equals the W that we want over the Q that we changed to coulombs because J goes with C. Cross multiply, and you get 8 times 10 to the negative 19.
Wait, if it said,
Say it again.
if it said 2 elementary charges,
Then I'd do 3.2 times 10 to the negative 19. And the last one, we have a 1.5 volts V. It's completely recharged. Each electron, well, this is tough. Do we use 1.6 times? This is a very mean question. Do we use one elementary charge, or do you use this? Well, I don't know. Let's try one of them. This is a super tough question. What is the minimum energy, W? Let's just use one. Let's see if this works. V equals W over Q. 1.5 volts equals W. Let's try, W is the unknown. Q, what if we did 1.6 times 10 to the negative 19? Would that work? Do we have an answer that's 1.5? I don't think we do, actually. So I realized that that's not the unit. So I'm going to use one elementary charge. And I do have an answer. So it's 1. E goes with E. 1 elementary charge. So 1 cross multiply, and you get 1 point. Now don't choose this one because J goes with C and E goes with E. Elementary charges go with electron volts. And that is good. I think that's the whole thing. Do you have to leave then? All right, let me stop this and I'll look.